So today we're going to look at section 8.4, the integral and divergence test. These are really two separate ideas, both putting into the same section. So we're going to start off with some detailed look at this series, the series sum of 1 over n from 1 to infinity, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus forever on out. Now, our question is, does this series converge or diverge? And so remember, what we need to do is we need to take partial sums. So we need to take partial sums and see if the partial sums are getting closer and closer and closer to something. And so this is a little bit of a tricky series. So we might want to get some evidence, collect some evidence, and look at some partial sums and see what happens as the partial sums, as n gets bigger and bigger in our Sn. And what happens if we take the partial sums, then the partial sums do something like this. They get bigger and they get bigger as we expect, right? Because we're adding more and more and more as we continue on. But and it seems like so we're graphing our partial sums here. They get bigger, but they get bigger at a slower rate. And so the question is, does this level off, right? If this levels off and it has an asymptote, if the partial sums approach something, then this series converges. If this in fact goes up and up and up forever, then it diverges and the sum is infinity. And so that's our question. And so this is a really tricky one to handle, because even if we actually look at some really huge partial sums, right? So maybe if we looked at something like the partial sum s sub 10 to the 46th power, right? That's a huge partial sum. Right? So that's 10 with 46 extra zeros after it. And so we've added up that many terms. As it turns out, this is still less than 100. So we've added up a huge number of partial sums of terms. We still get something that's less than 100. And so that suggests that this might converge, because we've added up so many things and we haven't gotten very big. But we still have to be careful, right? Because we're not sure what's happening, because we can't say precisely at this point whether it levels off or maybe it just grows so slowly. And so our idea here is we're going to think about this in a little bit of a new way. And so here's what I want to do. I'm going to think about this function 1 over x. And if I thought about this function 1 over x, well, then the height, I haven't drawn this particularly to the scale, but if I input 1, then the output is 1. So this height is 1. I'm going to draw some boxes. And this length is 1. So this area is 1. 1 times 1. This height, if this is at x equal 2, this height is 1/2. The length is still 1 because we're going from 2 to 3. So this area is 1/2. The height of this one is 1/3. The length is still 1. So this area is 1/3. And so we can continue on out making these boxes forever. But notice that if I would add up the area of all of the boxes, right, so all of these areas together is going to be 1 plus 1/2 plus 1/3 plus 1/4 plus forever on out, which is the sum of 1 over n from n equals 1 to infinity, which is the series that we were asking about. So notice that the area of these boxes then is in fact the series that we're asking about, but I can also say that from stuff that we've learned before, back in 7.7, we know something about the integral from 1 to infinity of this function. we discovered that this integral diverges. So this is infinity. The total area under the curve, so the total area under the curve is infinity, and the total area of our series is made up of boxes which are always above the curve, which means that there's always some extra area each step of the way. And so that tells me that the series 1 over n from 1 to infinity is actually bigger than the integral from 1 to infinity of 1 over x dx. So this series from 1 to infinity of 1 over n is bigger than infinity because this is infinity. So this series diverges. And this is the heart of the integral test. To compare our series to a function that behaves the same way, and notice that if our series is always bigger than the function, then the function diverges, then the integral must diverge as well. So this is something that's important that we're going to see and use all the time. 1 over n diverges. The sum of 1 over n diverges. Notice that the series, the terms, go to 0. 1 over n goes to 0. But that's not enough for us to conclude that the series diverges or converges. This was the one where the terms go to 0, but they go to 0 not fast enough. And so the series itself still actually diverges. So even though we had a partial sum, the partial sum at 1 times 10 to the 46 was less than 100. As it turns out, if we add up all of them forever and ever and ever, the series actually goes to infinity. We're going to look at something similar for 1 over n squared. So let's apply our same sort of thinking to the series 1 over n squared from 1 to infinity. So 1 over n squared from 1 to infinity. If we were to graph the function that behaved like 1 over n squared, well then we'd be graphing the function that is 1 over x squared. Because at 1, 2, 3, 4, 5, and so on, 1 over x squared behaves just like 1 over n squared. But now we see we have a little bit of a problem. Right? Because if I were to actually do exactly the same thing as before, I could, so far it looks okay, right? Because the area of these boxes, this is now 1, this is 1 over n squared, which is 1 over 4, this is 1/3, so the area of these boxes becomes 1 plus 1/4 plus 1, that should be 1/9, 1 over 3 squared, 9th, and so on, which is the sum of 1 over n squared from 1 to infinity. But according to our picture, what we have then is that the sum of 1 over n squared from 1 to infinity is actually bigger than the integral from 1 to infinity of 1 over x squared. The problem is that this integral is finite. This is finite. So all that this picture shows is that this series is bigger than a finite number, which means it might be a bigger finite number, or it might be all the way to infinity. So our picture here is no good at actually deciding whether or not this series converges or diverges. But we can be clever and make this into a picture that actually works for us. This improper integral converges. If I want to make any conclusion at all out of something like this, I would actually need to be less than this integral so that I can conclude that it's less than a finite number, which is therefore finite. So the only way to get less than a finite number, or less than, out of this picture, is to make my boxes that are so that they're below the curve rather than above the curve. And so that's what we're going to do. All right, so we're actually going to make this picture very similar way. But all that I'm going to do is, rather than draw my boxes above, I'm going to go left and draw my boxes below. So by drawing my boxes to the left, the area of these boxes hasn't changed. This one is still 1 times 1, so that has area 1. This one is still, now the height here is 1 over 2 squared, which is 1/4 times 1, so that's still 1/4. This one is 1/9. This one is 1/16. In order though to actually do anything useful for this, I still need to just integrate from 1 to infinity, because I can't integrate from 0 to infinity because it's improper on both sides. But what I can say then is that the sum, so if I'm only integrating from 1 to infinity, I have to ignore that very first term. Right? So I have to say that the sum from n equals 2 to infinity of 1 over n squared, based on this picture, is strictly less than the integral from 1 to infinity of 1 over x squared dx. Because really at this point what I'm looking at is just from 1 to infinity, and because I drew my boxes going left, I have to start at the second box in order to make those things match up. Alright, so that tells me that this is finite. This is finite. So this thing is strictly less than infinity, so this thing is less than infinity. So I can conclude that 1 over n squared converges. Well, so I conclude that 1 over n squared from 2 to infinity converges. But if this converges, then it's finite. And then if I started with the first term, I've just added a first term, which is a finite number. So I can actually conclude that 1 over n squared from 1 to infinity converges as well. And so putting this all together, we're not going to go through a whole proof of this entire thing, well, really of much of it at all, but what it tells us, we can make a similar argument to get the following theorem, which is called, really just called the integral test. For a series, sum of an from 1 to infinity if f at x is a function, we're going to have a couple of requirements on this function, such that 1, f at n is an for n equal 1, 2, forever on out. That is, the function behaves just like the series on the integers, on the natural numbers. 2, f at x is decreasing. We need that rule for some technical reasons. We can't have the function match the series on the integers, but then do funny stuff in between. Because if it does funny stuff in between, then I can't say exactly what's happening. I need it to really match the series and then interpolate nicely in between. So it's got to be decreasing the entire way. Then, the following is true. The series an converges if and only if the integral from 1 to infinity of the function converges. So in other words, the series behaves exactly the same way as the function behaves as an improper integral. For example, what about the series 1 over x 1 over n ln n? We can't actually start at 1 here because ln of 1 is 0, so we can't have 0 in the denominator, but we can start at 2. So where we start, remember, is irrelevant. As far as series are concerned, all I care about is what happens in the long run. The starting point doesn't matter. So, does this converge or diverge? Well, if we look at the integral test, well, so we need to see what happens, right? As n gets bigger and bigger and bigger, then this denominator, this part gets bigger, and so does this. So the function f at x equals 1 over x ln x is decreasing. That's good. So the first thing is satisfied. Second, this by design recovers the series on the integers. If I plug in 1, I get the same thing if I put it in here, or 2, or 10, or any integer. So then we just need to look at the integral. Again, we can't start at 1 because we get 0 here, but that's okay. I can start at 2 just like I start at 2 here, and say what happens to this. Well, this is one that we actually looked at before. This is something that I can integrate. I can actually integrate by u substitution, because if u is ln x, then du is 1 over x dx. And then I have the 1 over x dx right here. And so this becomes 1 over u du, which is ln absolute value of u, which is ln x from 2 to infinity. But when I plug infinity in, I get infinity, I get ln of infinity, which is infinity, which means that this series diverges. Example, series 1 over e to the n from n equal, this one we can actually start at 0 even if we want to, because e to any power makes sense. So we compare this to the integral of 1 over e to the x dx from 0 to infinity, which is the integral of e to the negative x dx from 0 to infinity. But this integrates to negative e to the negative x from 0 to infinity, which is negative. But what happens when I put infinity in? Remember, really what we're doing is taking a limit. When I plug infinity in, I'm getting e to the negative infinity, but e to the negative infinity is 0. So I get 0 minus e to the 0 is 1, so minus 1, which is 1. So this integral converges, so this series converges. And so the punchline is, if I want to apply the integral test, I take the series, I convert it to a function. I can also say that this is a decreasing function because as x gets bigger, e to the x gets bigger, so the denominator is getting bigger, so the whole thing is getting smaller. This series, this integral converges, so the corresponding series converges as well. What that means is that I can say for sure that as far as p series are concerned, right, so a p series is just like a, well, it's a 1 over x to the p. It behaves like 1 over x to the p. I mean 1 over n to the p, where n starts at 1 and goes to infinity. Well, remember, our 1 over x to the p dx from 1 to infinity, this converges as long as p is bigger than 1. So this converges for p strictly bigger than 1. Any p value bigger than 1 will make this converge, which means that this converges at the same time for p bigger than 1. Not equal to 1. If I put p equal to 1, that's 1 over n, which we already discovered diverges. Lastly, for today, we need to look at what we call the divergence test, which is just a big word for a pretty simple idea. And it says this: if I'm looking at this series AN, if the terms of this series don't go to 0, if the limit as n goes to infinity of AN is not 0, then there's no way that this series can converge. Because if the terms go, if these terms are getting closer and closer and closer to 2, say, then near the end of the series, I'm looking at 2 plus 2 plus 2 plus 2, which is going to go all the way up to infinity, for sure. So if the terms of the series don't go to 0, then there's no other choice but to say that the total series, the sum of AN, diverges. This is an if-then, so notice that if the terms do go to 0, this doesn't say anything at all. So our three options for a divergence test, well, I really have two options. I can use it to conclude that a series diverges, or I can say that it's inconclusive. So what does divergence test say about the following? What does it say about this series, 1 over n squared plus 3n, where n starts at 1 and goes to infinity? Well, the limit as n goes to infinity of the terms, 1 over n squared plus 3n, is 0, because as n goes to infinity, this denominator goes to infinity, so this is 0. All that the divergence test says is if the terms don't go to 0, then I can make some conclusion. The terms do go to 0, so I can't make any conclusion, and we say that it's inconclusive. I cannot make any decision based solely on the divergence test. But I might be able to make a decision on some other grounds, but not on the divergence test. What about this one? Well, in this case, the limit as n goes to infinity of 2n plus 1 over 3n minus 1. Well, now as n goes to infinity, I'm looking at the biggest degree terms, and I see 2n over 3n, which is 2/3, which means these terms don't go to 0. The terms get closer and closer to 2/3. So near the end of my series, I'm looking at 2/3 plus 2/3 plus 2/3 over and over and over again. I'm adding up the same thing over and over and over again, which is not. So that means that I can conclude that since the terms don't go to 0, the divergence test says that the series actually diverges. All right, and that's the basics of 8.4. See you next time.